Hey guys and gals, next little topic at your request is to talk about similar triangles a little bit and how we solve similar triangle situations. So we'll start off with a simple example, and then we'll do an example from the practice test. So the first question, or the question that we have over here, well, there's no question, but essentially if we're given two triangles like this, where one has a couple sides, 10 and 6, and the other one has a couple sides also, 12 and x. The goal will be, well, what is x going to be? How do we find x? And first off, to talk about what similar triangle means. Two triangles which they should look the same. In this case, like this one looks a lot like this one. Just looks like maybe this one is the same as this one, maybe a little bigger. Actually, to me, it doesn't quite look like they're exactly the same in shape. But the definition of similar triangles would be two triangles that have all the same angles, meaning all three of the interior angles. And remember, interior angle just means the measurement of how many degrees are each of the angles in there. All three angles have to match one another in order for them to be similar. So these two triangles would be similar because A is the same as A, and this is kind of how we write that. If we draw a single line there, it's called a congruent angle, two angles that are the same. B is the same as E over here because they both have two lines. Again, that is the implication that they're congruent. And C and F would be the same because they have three lines. Essentially, in this drawing, we're just assuming that the three triangles have all the same angles and they're basically the same shape. But if you can imagine, there's the first little triangle, BABC, and then there's the bigger one, DEF. It's just sort of been blown up. If you can imagine taking the image on your computer of ABC, clicking the little box in the corner to just make it bigger and scale it exactly without distorting the size, that's kind of the idea of what it means to be similar. And so what's nice about similar triangles is all the sides within two similar triangles must be proportional. And so we've been talking about proportions in class, but what that means is the ratio of these two sides must match with the ratio of these two sides, and also the sort of how much 6 to 12, the ratio of how 6 to 12, the ratio of 6 to 12 must match the ratio between 10 to x. Essentially, something's happened from 6 to 12, and that same thing must happen to go from 10 to x. And well, you might be thinking, well, if this one is 6 and this one is 12, that side over there is twice as big as that one. So if they are indeed proportional, that same pattern has to trend towards AB to ED. Basically, this one is twice as big as this one. This one must also be twice as big as this one. So, and remember, with proportion problems, it's never a plus minus thing. It's always a multiply or divide thing. So even though 12 is 6 bigger, like if you added 6 to it, that would get you there. You can't just add 6 to 10 to get the other side. That would not be good proportional reasoning. So proportional reasoning requires you to multiply. In this case, 6 times 2 makes 12, so 10 times 2 must make 20, and so this side right there has got to be 20. Or you know how I showed you to do it in class would be to start with this to start with your two triangles. So let me just draw those two over here, and here's our bigger one. If this one is 10 and this one is 6, this one is x, this one is 12, then if we're what we could do is we could simply write a proportion to solve it because they're proportional. And similar triangles must be proportional, so we can use a proportion to solve it. So remember, proportion is this set of two equal ratios. A over B is equal to C over D. Or essentially we want to write a fraction is equal to a different fraction. In this case, we can do this one over this one. So 10 is to x as 6 is to 12. And how we say proportions is first is to second as first is to second. And so in the case, the left side of the first triangle must be the ratio of 10 to x must be the same as the ratio between 6 to 12. So we could write out the proportion 10 is to x as 6 is to 12. And then we could solve from here by solving a proportion. So as we talked about in class, any proportion you can solve by using cross multiplication. Essentially, each denominator in our fraction multiplies to the opposite side. And so what we would get would be 12 times 10 on the left side. 12 times 10 is 120. And then on the right-hand side, we'd have x times 6. And since we don't know x, we would normally write that as 6x. X times 6, or 6 times x. And so we get 6x equal to 120. And then after we cross multiply, we divide by the coefficient remaining. So in this case, after that x multiplies over to the 6 right there, we're left with 6x. And if we want to solve for x by itself, we have to divide away the 6. To cancel out a multiplication, we have to use division. So we divide both sides by 6, and that leaves us with 100x is equal to 120 divided by 6, which is 20. So I kind of said that earlier. I said that the other side must be 20, but this kind of gives you another way to go about it. If you like the whole proportion and you can make sense of proportions and you already know how to solve the proportion. And again, sort of the shortcut that I was saying was that from 6 to 12, we would multiply by 2, and so that's, it's kind of like we blew it up by a factor of 2, and so the same factor of 2 would have to be multiplied by the original 10 over there, and so x would have to be 20 if it is indeed that same proportion. And again, since the angles were the same, had to be the case, and so that's one idea. But so it's not always, you can't always solve it like I just did in blue there with a shortcut, because sometimes the sides might not be directly you might not be able to multiply one to get the other quite so simply. It might take a fraction or a decimal or something more difficult than just multiply by 2. And so the example from the practice test, let's look at this one next. So on the practice test, you're given two triangles like this, where this side is labeled as y and this side is labeled as 12, and then another triangle of similar shape over here, where this side is labeled as 18 and this side is labeled as 6. And what the directions of the question say is the following triangles are similar, solve for y. So again, you need to know they're similar. In this case, they kind of look like they're the same shape. One's just bigger than the other. So the fact that they're similar means that the sides are proportional to one another, and that means we can use the proportion to solve it, all that same thing. And so what I was sort of saying before is that the trick where I use to figure out what multiplies by 12 to get 18 isn't quite as easy, because 12 doesn't multiply by any whole number to get 18. You might be thinking, well, times 1.5 or 3 halves, and that's good. If you could do that, you could do the same thing to find y. However, we would have to do it backwards, because we don't know the starting side y. So if we were trying to figure out y from 6, you would actually want to divide 6 by 1.5 or multiply by the reciprocal fraction 2/3 to get the original side. So that shortcut would indeed work, but in this case you'd have to flip around your reasoning, because which side is proportional. Anyways, I think it's just easier to make sense by using a proportion setup. So again, how we would do it, we would say, well, this side and this side would have to be the same ratio as this side to this side, and that's the idea. That's what we mean when we say it's proportional. So we would have y is to 6 as 12 is to 18. And again, we compare on the left side the sort of this one side of this triangle to this side. So we're comparing the same sides to one another on the left-hand side. And then on the right-hand side of the proportion 12 to 18, we compare again in the same order, those two sides to one another. So we do this one is to this one, so left to right, and then this one is to this one, again left to right. If you flip it around, if you went backwards, that the whole proportion would not work. So got to make sure to pair up the correct sides. So anyways, now once you have your proportions set up, we can solve it again by cross multiplying. So we would have 18 times y on the left side, which we would write as 18y, and then 6 times 12 on the right side, which 6 times 12 is 72. And then finally, as with any proportion, we would divide by the coefficient. So we divide both sides by 18, and that would give us that y is equal to 72 divided by 18, which seems like it's 4 to me. And you can check on that if you want by doing long division or calculator. But 18, 36, 54, 70, yes. So it does go perfectly into it 4 times. But anyways, what we would get would be y is equal to 4. So this side over here, the original side in my diagram, was 4. And that seems, to me, it seems right because from 12 to 18 it got bigger, not multiplied by 2, but smaller than that. And if y is 4, this one here, again, going to 6, it is getting bigger, but not doubling. Actually, in this case, it's going by 3 halves. It's growing by 1.5. So 12 times 1.5 is 18, and 4, our answer for y, times 1.5 is 6. So it sort of should, in the end, it should make sense. Some of you may have been thinking, well, couldn't you have used the Pythagorean theorem, that other thing we just talked about, to solve some of these sides, since we know some of these sides over here. And one thing with the Pythagorean theorem is these triangles are not right triangles. So a right triangle, remember, has an angle like this in it, a right angle, and these ones do not look like. Well, maybe this one might look right on the bottom, but if you don't know for sure that it's right, don't use the Pythagorean theorem. In this case, similar triangles, be thinking of something else, be thinking of proportional. And actually, this sort of idea works for other shapes too. Like if you took a rectangle and you compared it to a larger rectangle with the same sort of proportion, if they were similar, they'd be proportional, and you could use the same logic to find the other sides. Or any shape at all should obey this basic idea if they're similar in this sort of way. But we don't define any other shapes this way. Just similar triangles have the same angles and are proportional to one another. Let me know if you have any questions. Either email me, post in the comment board, click like if you like it. See you guys in class.